Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O-Levels Physics 5054. Today we have set our hearts to solve ATP paper. We call it paper 4, and for this purpose we have selected October-November 2010 4-2 paper. This paper 4 or this ATP paper belongs from the zone 2. So the time allotted for this paper is 1 hour. So let's start this paper. So here we go. So on your screen, you can see the paper is showing up October-November 2010 for 2 paper, alternative to practical ATP paper. We also call it paper 4. So here comes the question 1. A student investigates the movement of a suspended meter rule. Meter rule A is clamped horizontally above the bench as shown. So they have a meter rule, for example. This is a meter rule, and it is being clamped by both the ends, and it is held by both the clamps. So it's horizontal and it's in air. And this is the bench, and they want us to meter rule them. Describe how the student checks that A is horizontal. You may draw on the figure 1.1. So very simple method. What I will do, I will take a vertical scale, and with the help of the vertical scale, I will check the height of the right end of the meter rule A from the bench. I will check the height of the left end of the meter rule A from the bench. If both the heights are same, that shows that the meter rule A is exactly horizontal. To make sure that the scale here is vertical to this bench, I will use set square, one set square at the bottom to make sure that the vertical scale is exactly vertical, and one set square will be used here to mark the position of the bottom of this meter rule. So I have written this answer as well. So let's have a look at how I have written it. So here we have my answer. So by using the vertical scale and a pair of set square as shown in the figure, height of both ends of the meter rule from bench is measured. If both ends have the same height, meter rule is horizontal. And this is that diagram. So you can see I have put a vertical scale here, I put a vertical scale here, put a set square like this, put a set square like this. You will be by this, you will make sure that the vertical scale is horizontal, vertical to the bench. And by using this, you will be able to measure the height, exact height of the bottom of the meter rule A. So this is my answer. I hope you understand. So let's have a look at the marking scheme. And here we have the marking scheme. Okay. What does the marking scheme says? Use of the spirit level. You can also use the spirit level. You can use the plumb line and set square. Check height at 2 points on rule, at least 5 centimeter apart, same distance above the bench. Allow answers on the diagram. So our answers are right. We have also worked on the diagram. This was a 1-mark question. Then he says a second meter rule B is suspended vertically from A by 2 strings of equal length. Both strings are placed at a distance D from the center of the meter rules as shown in the figure 1.2. So this is the center of the meter rule A, and here we have 2 strings. By these 2 strings, this meter rule B is hung with the meter rule A. So this is meter rule B, this is the meter rule A. These are 2 strings, and from the center, their distance is same. Their question is, describe how the student checks that the 2 strings are equal distance from the center of the meter rule B. Okay, so what you can do, I can measure the distance of this, the string which is on the right from the end of this meter rule, from the right end of the meter rule B. Also check the distance of this string which is on the left from the left end of the meter rule B. If both these distances are equal to each other, that means the strings will be at equal distance from the center of the meter rule B. Another method can also be that you can measure the distance from the center of the meter rule B. You can measure the distance of this left string, and you can, from the center of the meter rule B, you can measure the distance of the right string. If both the distances are equal, that shows that both the strings are equally spaced from the center of the meter rule B. Mark center of the meter rule B. Check distance of each string from the center of the meter rule B. If both distances are same, strings are at equal distance from the center. This is my answer. So let's have a look at the check strings at 50 centimeter plus minus D. Measure both D from center ends, or you can do this thing from the ends of the rule B. Hopefully you understand. This is my answer. Okay, so we are going to the question number 1. It's C part. B is made to rotate backwards and forwards through a small angle in a horizontal plane about its center, as shown in the figure 1.3. This is the view from the above. So this is the meter rule A. This is the meter rule B. So this will swing like this. The meter rule B will swing like this. Okay. This is the meter rule A, and this is the meter rule B. So the meter rule B will be swinging like this. They have taken the top view. The student determines the time T for B to rotate once forwards and then backwards. On the figure 1.2, mark where the eye of the student is placed to observe the rotation. So if you want to check the rotation, so the eye must be placed here. So the eye must be placed here. So here you should have the eye of the observer exactly in front of this position. Okay, describe how the student determines the T accurately. So you will swing the meter rule B, and after 2-3 swings, when the swing becomes smooth, the swinging becomes smooth. When it is at the center, then start counting. It comes here, then goes back, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So count 10 swings, use a stopwatch, and when you start counting, start the stopwatch. After the 10 swings, stop the stopwatch. Okay, so you will get the time for 10 swings. Then divide that time, whatever the time you get, with the 10. That will give you the swing of the time of the one swing. So this is a 3 marks question, and then you will repeat this experiment 3 times, and then you take the average of the capital T. So here you can see I placed the I, and here is my answer. See second part. He says the swing B, after few swings, when a meter B is exactly aligned with the meter A, you can mark this position on the bench. So you can, on the bench, you can mark the position. You can mark the position here with a point on the ground. And you can mark this position on the bench, start, stopwatch, and time 10 swings of the meter rule. Divide time for 10 swings by 10 to calculate the time for 1 swing. Repeat this 3 times and take average capital T. Avoid the parallax error by positioning I exactly near the mark on the bench and keeping the line of sight at the level of the swinging meter rule B. So this is the marking scheme of that question, and time several means n oscillations, and oscillations must be more than 5 and less than 40, and divide by n repeat and average. Use fiducial marker. Fiducial marker, you know, fiducial marker means the mark which you put okay. The fiducial marker means the mark which you put on the ground. So remember this word and its spellings also. Fiducial. Fiducial marker is the point you mark or a cross which you will make on the bench to mark the position or when both the swings are aligned with, both the meter rules are aligned with each other. Time from center, where speed is maximum. Smooth swings, for example, no obstruction. Same amplitude, ignore, avoid parallax error. And use stopwatch, plot graph of results. He's saying ignore, avoid parallax error. So I have written parallax error, avoid parallax error. Okay, so you can write a better answer. I hope you have an idea what they want us to write. Okay, question number one is D part. He says the T is determined for different values of the D. Value of the D and the T are recorded in the figure. So D is the distance of the string from the center of the B. So it's in centimeter. This capital T is the time for one swing, that is in seconds. So for 15, it's 2.74. For 20, it is 2.07. At 25, it is 1.63. For 30, it is 1.37. For 35, it is 1.18. And for 40, it is 1.03. He says on the figure 1.5, plot the graph of the T in seconds on the y-axis. This is very important that the T should be on the y-axis against the D on the x-axis. Start your graph from D10 and the T for 1 second. Draw the curved line of the best fit. Okay, so here we have that graph. So the time we will start from, he says 1 second and D from 10 seconds. Okay, 10 centimeters, sorry, 1 and 10. So let me show you. The D will be starting from the 10 and the time will be starting from the 1 second. Here you can see on the x-axis, we have represented the D in centimeters, and on the y-axis, we have represented T, which is in the seconds. And then I will plot those points at 15, the time is 2.74. At 15, the time is 2.74. And at 20, it is 2.07. So you can round it off a little bit at 22.7 and not 2.7, 2.07. It is 2.07. At 1.63, at 25, it is 1.63. At 25, 1.63, little bit round off you can do yourself. At 30, it is 1.37. At 30, it is, at 30, it is, at 30, where is that thing? At 30, it is, at 30, it is 1.37. And then at 35, it is 1.18. 1.18, and then you have at 40, it is 1.03. At 40, it is 1.03. So then you will join them with the line of the graph of the best fit. And this is what they have asked. Draw the curved line of the best fit. We are done with that. And then their question is, use data from the table to show that T is inversely proportional to D. Okay, so from the table, I have to show that D is inversely proportional to T, to the D. You see, if two quantities are inversely proportional to something, so if the D will become double, you see here, the D has become 2 times, it has become 2 times, so the time period must become half. If this will happen, if one quantity doubles, the other quantity becomes half, then it means that they are inversely proportional to each other. So we have to show this from the graph, by using this. Okay. When the D is 15, the T is 2.74. When the D is 30, so the D has become double. The T is 1.37. So when D doubles, T becomes half. So we can say they are inversely proportional to each other. So let me show you. This is how we have to show this. I hope you can see this. And then we have another question. And he says, suggest a reason why the values for the D smaller than 15 centimeter are not measured. So if you will make the D less than 15 centimeter, when you will swing the meter rule B, it will be not very stable. Okay, so when D is smaller than 15 centimeter, it becomes difficult to keep swinging meter rule B in balance. So long time to take readings, unstable swings, difficult to oscillate, rotate, allow T increases, ignore difficult to time, does not oscillate, rotate. Okay. So my point is that the swing, the meter rule B will be not very stable when the D value will be less than 15 centimeter. Hopefully you understand this. And now we are going to the question number 2. He says, a student plots a heating curve for water. The student places an electric heater in a beaker of water at room temperature, as shown in the figure 2.1. Okay, so here we have water. This is immersion heater. So this heater is basically submerged in the water. This is beaker. We have water. Here we have thermometer. The student measures the temperature of the water every minute for 30 minutes. So after each minute, he is noting down what is the temperature of the water. The student suggests using the second hand of a wall clock. So they are using a wall clock to measure the time. Another student suggests using a stopwatch. He's saying we use two stopwatch reading to 0.01 second, which means it goes up to 1/100th of a second. So just explain which timer is the more suitable to use, because we have to measure the time after 1 minute. So for that, the uh, the wall clock is better. Better means the stopwatch is more sensitive. It goes up to 0.01 seconds. We don't because we have to note down the temperature after every minute. So I don't need to go to that precision. I don't need that sensitive timer which can measure up to 0.01 seconds. So wall clock will be a better thing. So let me read you my answer, which I wrote. Then we will check it from the marking scheme also. Stopwatch measures up to 100th of a second, whereas wall clock measures up to 1 second. Temperature is checked after 1 minute. So for this, wall clock will be a better choice, because we don't need that sensitive. So let's have a look at here. Wall clock plus only need to measure to the nearest second, accurate enough. Time measured is large and stopwatch is easier to hold or closer to the apparatus. Ignore easier to use read reaction time, not stopwatch, as it is more accurate. So the stopwatch is more sensitive for this measurement. And so I don't need that precise time, because I need to measure the time after after 1 minute. I'm going to use the thermometer. So the wall clock will be measuring up to 1 second. That is enough for this thing. That precision, or you can say that is enough. Okay, the student draws a table to record the results, complete the headings. Here write the time and here write the temperature. The time will be measured in minutes and the temperature will be measured in degree centigrades. So you can see time in minutes and temperature in degree centigrade. So this is what we have to write here. You can see the marking scheme of question number 2B part is showing up on your screen. And then we have here, it says, the student, C part, question number 2C part, the student starts with water at room temperature and notices that the temperature increases for 20 minutes and then stays steady at 60 degrees centigrade. The student uses the data to plot a graph of the variation with the time of the temperature of the water. On the axis of figure 2.3, sketch the shape of the graph, obtain mark any known values on the graph. For 20 minutes, the graph will be increasing, and here you can see I am our temperature. Here is the time. For 20 minutes the temperature will be rising, but the gradient of this curve will be gradually decreasing, because the rate of increase in the temperature will gradually decrease. At the start it will be the rate of increase of the temperature will be larger, but gradually it will decrease, and after 20 minutes the temperature will remain constant, as they have said, so that this graph will become a horizontal line. Okay, so this is the marking scheme. You can read it from here. I have already checked it. So let's go to this is my answer. So we are going to the next question. He says, explain why the temperature of the water does not rise above the 60 degrees centigrade. So see, at 60 degrees centigrade, the heat gained by the water, which is coming from obviously the heater, and the heat lost from the water to the surrounding, which will be due to the heat lost from the surface of the water in the form of evaporation, and heat being lost to the surrounding by the conduction. And you see convection, conduction, radiation, the heat is lost from the water. And the rate of the heat gained and the rate of the heat lost, and they become equals to each other. That's why the temperature of the water will no more rise. This is my description. So unfortunately, the photo which I took is not that clear. Heat gained from the heater by water and heat lost from the water are equal to each other. So the rate of the heat gain from the heater is equal to the heat loss to the surrounding. So we have equilibrium. So now the temperature will become constant. So we are going to the next question. The next question is question number 3. He says a student performs an experiment to find out whether a coin is made of pure copper. So the student collects 20 identical coins and places them in a light bag. The bag is hung on a Newton meter as shown in the figure 3.1. So here we have 20 coins. The Newton meter is showing a reading of 1.5 Newton. This is one coin and this is actual size. Record the reading from the Newton meter to find the weight of the 20 coins. It is 1.5 Newton. So here we have it is 1.5 Newton. So it's 1.5 Newton. 1.5 Newton is the right answer. Okay. So then we have a full-size diagram of a single coin is shown in the figure 3.2. Measure accurately the diameter D of the coin. The diameter of D, take a scale and check how much is this diameter. Whatever the reading you get, just write it here. I have done this and I found it to be 2.5 centimeter. So 2.5 centimeter is 2.6 plus minus 0.05. Because this of the photocopy, the diagram has little, whenever you photocopy a paper, the diagram shrinks. So that's why whenever we measure the length, it's a little bit smaller than the accurate value. So our answer is right. He says, then he says, the average thickness T of the coin is 0.19 centimeter. Describe how to measure T accurately. Okay, so if you want to measure it accurately, you can measure it with the help of a vernier caliper and directly, or what you can do, you can use a micrometer also, and you can also use, you can put 3 or 4, 5 coins, make a stack of 5 coins, and then with the help of the vernier caliper, measure what is the thickness of the 5, then divide that thickness with the 5, you get the thickness of 1 coin. And this will be more accurate method. Stack 5 coins on each other, measure the thickness of 5 coins with help of a vernier caliper, divide this thickness with 5 and you will get thickness of 1 coin. Repeat this procedure 3 times and take the average. This is my answer. Measure N and divide and repeat, check vernier caliper, micro screw gauge or rule with the millimeter markings, measure pile of at least 10 coins and divide by 10. So this is the same answer. Okay, so we are going to the next part. It is question number 3 and it's D part. And what they say, the density rho of the metal used in the coin is given by the relationship 20 W20 divided by pi D square T. Calculate D. We have the value of this. We have the value of the D. Just put these values and just measure it. So here you go. We have done this and you can see this 20 multiply 1.5 divided by pi divided by 2.5 square divided by 0.19 and you get 7.4 grams per centimeter cube. 7.4 grams per centimeter cube is the right answer. This is my answer. Okay, so where we go, question number 3E part, he says copper has a density of 8.96 grams per centimeter cube. State and explain whether the coin is made of the pure copper. The coin's density is 7.4 grams per centimeter cube, whereas the pure copper density is 8.96 grams per centimeter cube. That shows that the coin is not made of the pure copper. There is something mixed with it because the density is not same. So my explanation is density of coin, the different, sorry, I wrote the different. The density of the coin is different from density of pure copper. So the coin is not pure copper. So, and this is, okay, so our answer is not. So we go to the next question. He says a student is given two identical steel bar magnets A and B as shown in the figure 1.4. The student is asked to determine which magnet is stronger. So what I will do, he says the student is given a list of apparatus available for use in the experiment. Describe how to determine which magnet is the stronger. You should include a diagram to show how your apparatus is used. Apparatus chosen, then diagram, and then explanation. And it's a 3-mark question. So very simple. It's a simple experiment. This is the diagram and the clamp stand, clamp, boss, magnets, Newton meter, plain paper. So what I will do, I will, with the help of a clamp stand, I will hold a piece of iron. Uh, so then I will, meter rule, boss, magnet, Newton meter, iron bar. Yeah, we have iron bar here. I have not written here iron bar, just note it down. So I will hold the iron bar with this stand. I will put some papers here. And then I will put a magnet here. For example, the magnet, there are magnet A. And I will hook it. And we believe that there will be a hook. And then we will hook a Newton meter with it, and I will pull it upward, and I will note down the maximum force which is recorded here before this magnet is separated from this iron. For example, you have put here 5 pages between. So why we put pages? So make it easier. So then do the same thing with the magnet B. Same apparatus, same everything, 5 pages here, magnet B here, hook it with the Newton meter and pull it and note down the maximum force which will be recorded here before this magnet is separated from a piece of iron. So the magnet which will take more force to separate from the iron bar, and that will be stronger magnet. That's the simple procedure. So our idea is place some papers between the magnet and the iron, pull the magnet upwards and note maximum force needed to separate the magnet from iron. Magnet which requires more force to separate from iron is more stronger. So this is my answer. Experiment that would work, diagram apparatus not. So you can read this. I have already done this. So you can pause the video. You can take this, read this. Okay. Then their question is 1-mark question. Question number 4B part. He says the student finds an iron bar that looks identical to the magnet. The magnet and the bar magnet mixed up. Describe how the student using only the magnets and iron bar would determine which of the 3 is the iron bar. The bar which is being attracted to other bars, is both ends are attracted to all the ends of the other bar, is iron. And the bar whose one end is attracted and the other end is repelled by one of the ends, that is a magnet. Because you see the repulsion, if the two bars are magnet, then for example, south they will repel each other, north they will repel each other. So if a bar is repelled by a magnet, that shows that this bar is a magnet. If the bar is attracted to a magnet, it does not mean it is also a magnet. It can be a magnetic material. So repulsion is the actual test which shows that so I try to write the answer. Bar who is attracted to both ends of magnet is iron. Bar who is attracted to only one end of magnet and from the other end is repelled is a magnet. Bars which can repel each other are magnets. Bars which is always attracted to other two bars is iron. So the bar which will be repelled, that will be a magnet from another bar. So So my dear students, we have reached the end of this paper. And, today we have done October, November 2010, 4-2 paper. This was an ATP paper, alternative to practical. I have tried my best to explain you the concepts. And I have also tried to use the marking scheme. It's my advice to you, whether I write the answer, whether your teacher write the answer, or you yourself write the answer. Always check them with the marking scheme. It's a very important habit. And it is possible that I might make some mistakes. I'm not a scholar. I'm just a humble student of physics. So just this video actually is a solution of this paper, and it is a way by which you learn how to answer these questions. And I always believe that you can write, my student can write a better answer. So thank you very much, everyone. I think it's a great blessing for me that I can make these videos which can touch the life of so many students around the globe. Please share the link of this video if you think this can help you, your students, your class fellow, your siblings, your juniors, your seniors, your teachers. Please share the link of this video onto your Facebook, onto your Twitter account, and onto your Instagram. Thank you very much. Have a good day. God bless you all.